Hey, welcome everybody here. Welcome to our fourth and last of our mechanical waves. In fact, let me take a moment, or last of our lab on mechanical waves, I guess is how I should say it. Let me repeat it because it's worth repeating, that this class is a little different than the other physics classes in the sense that we don't do the same topic the whole semester. It's best to think of this class as like 4 mini classes. And so this beginning part, we try to go very quickly through the mechanical waves. We try to do 4 chapters in 3 weeks, and this is our fourth and final lab on mechanical waves. And it's a little more computer-oriented today than most labs, although, I don't know, being online, maybe that doesn't matter because that's kind of how it ends up being for you, is computer-oriented, where you watch me, doing the video here. But it's a really neat lab, and like I said, it's the fourth and the last one, and then we're going to move into our thermodynamics starting with the next lab. But the title of it is on page 10, and so let me encourage you to open your lab manual in your PDF to page 10, and you'll see the title says Complex Waves and Superpositioning. And the idea of this lab is to drive home, I think, one of the harder topics of these 4 chapters. At least in the past, that's what I've discovered, is students kind of have a hard time kind of understanding what we mean by complex waves. So let me take a moment before we begin this lab and just kind of point out the difference between what we'd call a simple wave and a complex wave. All right, let me start mathematically. So we've been learning in class that if you were to write out a mathematical description of a wave, where y represents the vibration of it, you have this amplitude, then you have this trig function, sine or cosine. We could use either one. Remember, they're just offset by a phase, and for better or worse, when we did oscillations, we chose to use the cosine function, and now when we do waves, we choose to use the sine function, and that just kind of helps us get our thoughts straight. But it would be this kx minus omega t, and then we can add a phase to indicate that the wave may or may not have started at 0, because you know that a sine function starts at 0 when time is 0. So if you have a wave where you define time equals to 0 and x equals to 0 and the wave is at 0 and it's on its way up, that would be a perfect sine function, and then your phase would be 0. If I were to draw a picture of this, and so let me draw the horizontal line first, because without drawing the vertical axis, I would have something that looks like this. That's what a simple wave would be. And of course, now I can choose where I want to put my grid, where I want to put my vertical axis, where I want to put my origin. But if I do it in such a way that I want phi to be 0 here, that would make it a pure sine function, and so that might be a good choice of where I pick the origin to be. All right?
What is the horizontal axis?
Huh?
Time or x?
Oh, so this would be y on the vertical axis. Thank you, Ron. And of course, on the horizontal axis, and this is what Ron's pointing out, so let me make it clear, this could be the x or this could be the time, because it's a function of either one. So it depends on which one you want to look at. Let me call it x for now, because we're going to actually do both in the lab. We're going to have one axis that is a function of time and another one that's a function of x. But we'll start with x, so I'll start my description this way. And so this would be that function. So a moment in time later, maybe I'll switch to blue, the wave would have moved on. And of course, the negative sign means it moves to the right. So I'll just kind of draw a wave. Let me do kind of this scenario. Whoops, sorry, did I mess that up a little bit here? No, it's, well, not done as well as I'd like it to be. But if you could imagine those crests moving forward, that's what would happen as a function of time. Okay, so this is our simple wave. And a complex wave then, and this is what I want to get at in case you missed it here in chapter 18, a complex wave is what you get when you have more than one simple wave. So two simple waves added together. So it may be something like this. In a mathematical pattern, y as a function of space and time is equal. And so maybe I'll just say amplitude 1, sine, maybe a wavelength 1, and a frequency 1, and some phase 1. And then, of course, added to that, maybe a wave of a different amplitude, and, of course, maybe even a different wavelength with a corresponding different frequency, and maybe even a corresponding different phase. Now, we're not going to do anything real complicated here in the lab, but this was that discussion that we had in chapter 18, and you hopefully saw on the lecture. In fact, maybe I should pause and say if you haven't done the chapter 18 lecture, do that first so you can get an idea of what we mean by simple waves versus complex waves. And so we would add them together. Now, in a picture form, maybe it would look something like this. Maybe the first wave looks something like this. And so I'll just say this is the x-axis. And I won't even worry about the phase, so I won't even draw the vertical axis. Okay. And then maybe the second wave is twice as long in terms of wavelength. So maybe it does something like this. And when you add those two together, those two simple waves together is a complex wave, okay? So we can get some very interesting patterns. In fact, they can get so complex that we call them complex waves, right? They can get so complex that they may not look like they're made up of a bunch of sine functions, but rest assured they are. In fact, you're going to hear me using some words called a Fourier transform. Some of you have heard that in your math class. I think that's covered in Math 220. Many of you are in 220. Probably most of you are in 220, so it's early in the semester, so you haven't done Fourier transforms yet. But no, that's the point. The point of the Fourier transform is to give you this mathematical technique to do what I'll call the reverse. I'm showing you two simple waves, and the result is a complex wave. But if you start with the complex wave, you can then break it down into its components and say, okay, here's a complex wave. What is it made out of? And so maybe that pole's there in the way, so I'm going to go maybe a little bit further here to draw this. And I probably won't do a good, accurate job of drawing it, but here's what we do. And let me throw another important word out there. It's the other word in this title, because the title of this, I'll say it again, is Complex Waves and Superpositioning. So when we take two simple waves and put them together, we just add the amplitudes together. In other words, positives go with positives. But if one's positive and a negative, they tend to cancel each other off. We call that the superpositioning. And it'll look something like this in this case. You can kind of see that we have this kind of up and down motion from the first one, and the second one goes up and down, but at a different rate or a different spacing on the x-axis. So if I were to guess, and again, this is probably not a real accurate drawing of it, but it probably looks like, to me, it would go up like this. And instead of maybe coming completely down, like this one is saying down, it's got this part still saying up. And so maybe it would look like this. Whereas when we get to this part here, this is saying up and this is saying down, and so maybe it's a little piece like this, but then eventually we get to this part where both of them say down, and so the result of that, of two negative numbers together, make a bigger negative number, and maybe look something like this. And that would be then what I would get as a result. Of course, and then it would repeat itself. So it would start all over again. And so I guess it would look something maybe like that again. And then repeat. And so something like that. Okay? And so that's kind of my guess at what these two simple waves might look like. But here's my point, and here's what we're going to do, and I hope this is what you got. If you ever saw something that looked like this, you're supposed to know that this right here, this is a complex wave. This is not a simple sine wave. You can just tell but visually that it is not a simple sine wave or cosine wave. And so what you could say is that this crazy pattern is actually made out of these two, or three, or four, or five different waves. And that's what we're going to be studying here in the lab. And I should say measuring in the lab to try to convince you that things that look complex like this are really made out of a bunch of these. Okay? And that's the intent of today's lab. All right, so today's lab is really broken into two pieces, and so like I said, if you're looking there on page 10, I'm going to go ahead and do the first 5 first. That's kind of like the first half of the experiment, and then steps 6 through 14 are the other half and the more advanced half. And in order to, quote, see these, we're going to really put the data into a computer and really make plots more than anything else. Now we are going to make some real waves in part 2. And so this little device that you saw in the third experiment where we did the speed of sound actually produces some waves. And you might remember from the third experiment we fed this into a speaker system and we could actually hear the sound waves. And so we start with electronic waves that then made a speaker move, and then we got the sound waves. Now, you guys didn't do that face-to-face lab, obviously, but when we do these face-to-face, those sounds, everybody in the same room are really obnoxious. So in this lab, we kind of skip over converting them from electronic waves into sound waves. We just measure them straight in electronic waves. Well, I'm getting too much into part 2. Let me show you part 1. And so part 1 is this. Let me get my board clear a little bit. And it says, let's start by seeing this pattern. That is, we're going to take two simple waves, combine them together, and see what we get. Now, the one I just drew for you was two waves of a different wavelength. And we're not going to do that. What we're going to do here is what we did kind of in our first discussion in the lecture. Remember, I listed a bunch of different patterns we could put together, and the first one was the easiest one. So that's where we want to start. The first one is two waves that have exactly the same wavelength, the same frequency, they travel in the same direction, they have the same amplitude, but the only thing that differs about them is their phase. And so in a picture, it would look something like this. And actually, since I'm going to use the screen, why don't I come over here and say, all right, so in a picture, it would look something like this. And the second wave is going to have exactly the same wavelength, the same frequency, the same velocity, moving in the same direction, but it's going to be a little out of phase. So if I draw it out of phase, maybe I'll start it here, and it's going to go up to here, down to there, and so I hope I'm drawing something that looks like the same wavelength, the same amplitude, but shifted in phase. And we're going to add that together, and there's that fancy word. We're going to take the superpositioning of these two and see what we would get. So we're going to start with some simple ones and make some complex ones. And in this case, it's going to be more visual. That's the idea. Watch, I'll come over here to the screen here. So let me pull down the screen and turn on my computer, and let me encourage you now to turn on your computer. You probably already have it on since you're watching this video here. But we're going to start graphical analysis. And I just want to kind of follow these 5 steps. And you'll see that these 5 steps are really saying, let's take these 2 waves. And they take those 2 waves and they say, combine them together with different phases. And then print those graphs. In your case, make a PDF of it. All right. So let me remind you to go to those directions that I sent out on the first week on how to get to your virtual machine. Again, you don't have to use graphical analysis, but since the school provides that free of cost, and that's what I'm going to teach to. Okay, so you will have a desktop, and this is my desktop. Yours will look a little different because you have a student desktop, and some of these files I have saved, so yours won't look quite like that. But one of the programs that we've already used 2 times is right here called Graphical Analysis. And it's great for making plots. And so I'm going to do that, and I'm going to ask you to do the same. Maybe it would be really good if you kind of split your computer screen and you could still watch the video here over in the corner, but you could also start, if you go to a virtual machine, you can't really do that. Oh, yeah, you can. Yeah, you can. I'm sorry. Yeah, you can, because if you've already started it, you would have to restart it again in the virtual machine. All right, so start it again in the virtual machine because you would have to come over here and start your new browser. But let's follow their directions. Here's what they're trying to say here. In step 1, it says, let's just make a mathematical wave on our graph. And it says here, and you'll see the dimensions, they're labeled out for the size of this room. I know we're not face to face, but from one side of the room to the other side of the room is about 13.6 meters long. All right? And so we're going to pretend that our drawings up here, that our graphs up here represent a sound wave in here. Because it says, open graphical analysis and make a column for position. Start your position at 0 and increasing it at steps of 0.136 meters until you get to 13.6 meters, which is eventually going to be 4 wavelengths. So I don't know if you can pan this, Ron, here, but basically here's what the mental picture I want you students to have, that we're going to pretend like there's a big sound wave in here, okay? And the wave comes out and maybe ends right here. So here's wave 1. And then, or wavelength 1. And then here is wavelength 2 for this first wave. And then, well, I made those too big. I got too close. But anyways, I think you get the idea. There would be a third one, and then there would be a fourth one here. Okay? And so that's going to be our 13.6 meters. So the first thing we really just need to do is to make a graph that would go from 0 to 13.6 meters. And that's what this is saying here. So I'm going to show you a little feature in graphical analysis that you haven't used before. Let me go ahead and click here on the X and get a little dialog box. Now this part you've seen before. The default is to call it X, and I'm going to leave that alone. Short name is X, that's fine. In terms of units, I'll measure everything in meters, so that's cool. So let me just put an M here for meter. But what I'm going to show you new here, at least new to this semester, you might have seen it in other semesters, but I'm going to put a little checkbox here that says go ahead and let the computer fill in all the numbers, and you've got a starting and an ending in your increment. So we are asked to start at position 0 and go to 13.6 meters. And they would be in size of 0.136. So you can kind of see it's 100 little divisions for each, or total of 100 divisions across this room. And so if I click done, you'll see, you can do the same here, a vertical column that's, well, we can't fit the whole thing on one page. I'll just kind of scroll down here real quick. But you'll see now we have an x-axis that increases from 0 to 13.6 meters. Okay? All right, that being said, now look at the next question. The next question says we're going to make 2 more columns. See, the 2 more columns, each column is going to represent these 2 waves that we want to visually, on our graphs, put together and see what we get. And we're going to take these 2 waves at 5 different phases. 1, 2, 3, 4, 5. Yeah, 5 different phases to see what we get when we combine them together. Starting with the easiest one where there's no phase in between them at all. All right, so here's what it says. Make 2 columns to represent the 2 traveling waves. We might as well make them at time equals to 0. Let me explain. If I come over here and I put down the equation for a wave again, y, which is a function of x and t, equals to some amplitude sine kx minus omega t plus a phi. If we go ahead and just say, let's draw the wave, or plot the wave is probably a better word, when time is equals to 0, we don't have to worry about that piece. Okay, so I'm not going to put anything with time in my plot. That's why I'll be just fine with x's only. Now, it does say here, make the waves of unit amplitude. Okay, so what they mean here is that I'm going to set my A equal to 1. All right, that just kind of really makes it a little easier to type it in. We're not really caring about the amplitude, that's part of it. All right, the big part of it though, right here, is we are trying to make the frequency at 100 and the wavelength of 3.4 and traveling in the same direction. So I put the minus sign, so I'm going to have a wave traveling to the right. And really the frequency is not really relevant because we're doing time equals to 0, but the wavelength is crucial. That's 3.4. And then it says make 2 waves to allow for a phase difference between the 2. So why don't I do this? Or why don't I call wave number 1 of unit amplitude, okay? Well, let me leave that alone. So wave number 1 would be of unit amplitude. The k value then would be 2 pi over 3 point, was it 4 or 6? 3.4. 4, yeah. Okay. Then times x. I don't have to worry about the time, and I just want a phase between them. So why don't I pick the first one as having no phase, whereas then the second one will be one that I can then adjust the phase depending on how they ask. And as I read ahead in here, it says make the second wave where first there is no phase difference between them. So I'll do that one first. Then they say do it again so that there's 60 degrees between them. Then do it again at 90 degrees between them. And then do it again at 120 degrees between them. And then do it again at 180 degrees between them. And so look at your results and hopefully it makes sense to you. And then of course you're going to, I was about to say print them. If we were face to face, we'd print them, turn them in. But for you guys, then you're going to save that graph and put it in a PDF. Okay, excuse me for a second. All right, so now let's make wave number 1. And so you go ahead and do this with me. Remember, and I'll go to the data column, and let's just call that a calculated column. You remember that's the one how we make something that is calculated. For the name, I'm just going to call it wave 1. Short name, maybe I'll just call it W1. The units, doesn't really make sense here, but I guess we could just say this would be the amplitude of 1, and if these were sound waves, this would be a distance that's moving. Now it turns out that if I put meters here, 1 meter of amplitude of sound waves, if you remember from the last chapter, 17, would be an enormously loud sound wave. I can't even describe how loud that would be. But nonetheless, I'm just going to put meters there just to kind of have something in its place. Actually, it's really bothered me. That's just too much. I should put, even millimeters would be too much. Nanometers, yeah. Nanometers. I'm going to put nanometers. All right. But you can put whatever you want or nothing. Okay, now, here's the big thing, the equation. So that's what I was trying to point out here on the board and give you a little more experience putting in equations. Go to your functions. In this case, it's a trig function, so I need to go down to the t's, trig. Then I get all my trig functions, and I can then look for the sine, there it is, and hit sine. And as I look at my equation, it looks like it's supposed to be 2 times, and I'm just going to put 3.1415 divided by 3.4 multiplied by, and so this is that variable x. This is what we want to plot across our x-axis. So there's x. So if I click done, you will see that it gave me a new column. Now, you may not be able to see it unless I spread out the graph here, and you can see all 3 columns. But, oops, maybe I'll make the graph smaller so we can see kind of the full table right now. And let me just make a plot. Now, remember the default is it plots x and y, and I didn't put anything in the x. The y. The default y column is a manually inputted, and I didn't even want that one. But let me select and encourage you to do the same thing to get an idea. Wave 1, and there it is. Okay, and so there is wave number 1. And remember, there should be 100 little blue dots here. I'm going to make a little change before I get too far. You can see how big these dots are. These are actually called point protectors. The dot itself is in the center, and then they put a round dot around it so it stands out a little better. Those are called point protectors. They make it stand out. But when you have a lot of them, it just makes it look like a fat line. And so I don't think this is a good option, although they're not quite running together. But they will by the time we go too far. So I'm going to go this. I'm going to do a right click on the graph and go to options. I think you saw last time me connect the points together, or maybe that was two labs ago. So I'll put the connect the lines, but I'll uncheck the point protectors. So hopefully what I will get now is just little tiny points, but lines drawn between them. Let me click done. Yeah, and I think that's going to be a little nicer by the time we do all of our graphs here. Okay, so here is that first wave. All right, now let's do a second wave. Okay, so let's do the same thing, and this time we're going to put wave number 2. All right, so maybe the thing to do is just, exactly copy what we did before, new calculated column. This time I'm going to call it wave number 2, short name W2, units, nanometers again. The big thing is this equation. Let's go to functions, let's go down to trig, let's go to sine, and then it's 2 times 3.1415 divided by 3.4 multiplied by the variable x, and then plus. And so that's the difference between our first and our second wave, plus some kind of phase between them. Now, on the board I just put a variable, but for a placeholder, why don't I just put the number 1 radian. 1 radian, if you remember, is about 57 degrees. So we're about 60 degrees. This is kind of the second one we're asked to do. But I'm just going to put a placeholder in here for now, and then click done. Okay, and so you can see, although maybe we'll need to make the table a little wider so you can see both of them if you want to. At some point they can get so big that we don't want to see the whole table because then our graph is too small. And on the, I think it was the second lab we did that. We had 18 columns and we didn't want to see all 18 at one time. We'd rather see the graph. But I think for this first part, we want to see all of them. In the second part, we don't. I think we got like 12 columns in the second one. But this will be good to see them all. So here's the position. Here's the two waves. Right now, of course, we're plotting just the first wave. It's in blue. But let's do the green one. Let's do the second wave. And again, let me show you a little bit of graphical analysis. This is where you want to click here. And as I said, if you just stick to here, you can only do one at a time. But if you click on the more, you got a little checkbox. So let's put both of them on there. See, and now you can begin to hopefully see, this is the point of the lecture and the point of the lab, is you begin to see now I have two simple waves, and I want to know what is the result when I put those two together. And so I'm going to use the principle of superpositioning, and then I'm going to have a complex wave once I just add them together. And so my next and last column for this first half is to make a new column. And at this point, I'm getting so many columns that I'm going to just shorten up my table so I don't have to look at all of them. But this new column, new calculated column, I'm going to call this the total wave. Okay, this is the result of those two. And maybe I'll just call it TW for total wave. And I'll stick to the same units, nanometers. But the equation is really simple. This is the idea of superpositioning. The superposition literally just says what would happen if you had the two waves. So let's take wave 1 and add it to wave 2. Okay? And so that's the idea. Superposition literally is just add them together. It is the algebraic sum of the two waves. And so what do you get? And so if I click done, it'll give me a new column there. And if I come over here and choose more again, I can plot all three on here. And it's this burnt orange color that I want to look at. The burnt orange color is the result of those two. And we said this in class, so if you missed it in class, let me say it again. But when we add two waves together like this, here's what we will get. We will get something that is also the same frequency and period and has a phase that is right in the middle of the two. You might remember the algebra that we did. Let's not do that again here in the lab, but the algebra we had the result of those two had a phi over 2 for the phase shift between them. And so sure enough, my burnt orange one peaks right in the middle of the peak of the green one and the blue one. And of course, the other part we did in class, we proved that it would have the same wavelength and the same frequency and travel in the same direction and travel with the same speed. And that's hopefully what we're seeing here. Okay? Now, the amplitude was a bit more complicated. If you remember, the amplitude it had twice the amplitude and then cosine of the phi over 2, the phase between them here. And so that's why I wanted to start this by showing you a phase between them. Now we can actually get to the lab, because the lab says you do this in 5 steps, and so you can see a progressive phase change between them. Look at them when there's no phase between them, then go to 60, then go to 90, then go to 120, and then go to 180 degrees between them. And those are the 5 graphs that will represent your PDF that you're going to turn in to indicate that you actually did this lab. Okay, and so those 5 graphs are the first half. Then we've got some more graphs to do. But those first 5 graphs will look something like this. Let me kind of run through them kind of quickly here. All right. So the first one is saying no phase between them. So I'm going to come over here to wave 2, double click on it. Remember, I put a little placeholder here of a 1. Let me change that to a 0. And so as I change it to a 0, that means my second wave has no phase between them. Now, I must admit, this one's a little bit hard to see. So before I hit done, I just want to come back. Notice it draws the green one first, then the blue one. But in this case, the green one and the blue one are exactly the same, so they're going to cover each other, okay? And you're not going to be able to see two of them. So it draws the blue one first, then it draws the green one over the top. So the only thing you can see is this green one. And actually, I think I can kind of see a little blue right there. So there is, I think, a little bit showing out of it. But notice then that the amplitude of this one is an amplitude of 2. In fact, I'm kind of wasting a lot of my graph space here. So maybe I should lower this to maybe a 3 or something. So I can maybe see things a little bit better. But this goes up to 2 and down to 2. And clearly this is showing what we worked out in class, that the amplitude would be 2a times the cosine of the phase difference between them cut in half. And of course we have no phase difference for this one. So that's what you're supposed to see, that this is essentially the burnt orange one is the complex wave. The burnt orange one is the sum of two other waves, and it's still by itself kind of simple because it is sinusoidal, but it's got twice the amplitude of the two. So we've got a nice wave here. All right, so this is going to be that first graph. Now, I thought maybe I would show you something because I got a lot of questions the last time we did graphical analysis of a good, efficient way of making this a PDF while you're in the virtual machine. So let me take a moment and show you what I do. This is not the only way to do it. This is my way, and I like it. So if you're looking for an easy way to make this a PDF, let me show you. Because sadly, graphical analysis, you cannot save in a PDF format. But what you can do is you can copy and paste it into Word and say that is a PDF. And that's what I'm going to do. That's the logic I'm going to do. So watch, I'm going to do this. So if I was making this lab, now remember, I've got a lot of more graphs. So this is just the beginning. This is just the first graph. I would do this. I'd say, okay, here's my first one. And so I'm going to come over here and right click on it and just go copy. And that's going to copy the graph. And then I would miniaturize it and come over to my word processor. I happen to have Microsoft Word on my desktop. I know many of you use Word, but others of you like Google Docs. It doesn't really matter. Use Google Docs if you like, but just come to a word processor and then hit paste. Okay? Now, if I'm turning in a lab, it might be nice to put a title here first and say, okay, lab number 4, complex waves and superposition. All right, so put a title there first. But then this is your first graph, okay? And I'll put a second one here in just a second and then show you how to make it a PDF. All right, so let me miniaturize Word here so we can come back to graphical analysis. And then let's just do the second graph. So under wave number 2, I want 60 degrees. Now, maybe the one challenging thing about this is I need to realize that I have been working in radians here. And the default for graphical analysis is in radians. So all that has been good. The author here tells me do it at 60 degrees. So I don't want to put 60 in here because that would be interpreted as 60 radians. So I guess I need to think a little bit. Let's see, the whole circle's 2 pi, so half a circle is pi. 60 degrees is a third of a half a circle. And so that's pi over 3. Okay, so let me put 3.1415 divided by 3. Okay, so pi divided by 3. I could even pick the parameter here. They do have a pi buried in here. But pi is so easy to type that I usually just type pi. Anyways, let me click done. And did you see it shift? I hope I didn't do that too quick. But as soon as I put it in, you'll see now that the green one has been shifted by 60 degrees. Now I just wonder here in my own, I put a plus. but maybe this is a good time, and I know I mentioned this on a couple of video solutions already. In your algebra class, if you had f of x and you wanted to shift it, you put f of x minus a. If you wanted to shift it by a, you put a minus. So maybe I should follow the author a little bit better, because he said shift it 60. See, notice how mine actually shifted a negative 60. So maybe I better do it the way the author says. Shift by 60 means I need to put a minus pi over 3. And I didn't really do that. And I just noticed it as I watched it shift. Okay, so to be a little more accurate, but we would get the same basic feel for it. Let me do that. Oh, good. So now you can see the green one is shifted to the right by 60. See, the green one it's been that way to the right. And I think that's what the author really wants, 60 degrees, not negative 60 degrees. All right, so I think that looks a little bit better. But again, you can kind of see where we're getting at. See how the amplitude is not quite as high anymore? It's not 2. See how it peaks at an average between the two? That's the visual picture I want you to get at it. That's how we read the math. That's when we saw those equations. That's what we were trying to see in our mind, is this picture here. Okay. So let's make this our second graph, and I'll show you the same thing here. Come over to the graph and first click on it to select it, then right click to go to copy, then go over to your word processor, which I picked Word, and then just do another paste. And so there is my second graph. If I scroll up, okay, so there's graph 1, and I'll scroll down, here's graph 2. All right, and so in a moment I would put 3. Now the truth is I'm not going to go that far. I'm going to let you do the 3rd, the 4th, and the 5th. But I do want to show you this. If you like this way, it's a really easy way to make a PDF, because once I have everything on one Word document or one Google Doc, all I got to do is say save as PDF, okay, and then email it to myself so that I can then upload it on Canvas, okay. Or you could access, now that I think about it, why not just access Canvas right in the virtual machine and then just send it up that way, okay? So kind of your choice here. But the big thing is the PDF. So I'm going to come over here and go to File and go Save As. Now Microsoft does have this button here, Save as Adobe Pdf. I've had some little troubles with that. So you can decide if you want to do it. But that's kind of a new feature in this version of Word. So I'm going to just show you as Save As, and just go to my PC. I'm going to go to my desktop here. The default name is Doc 1. Maybe I'll call it Lab 4. But it's right here under Save Type As. The default, of course, is Microsoft Word. Then I've got all kinds of options, but one of them is the PDF option. So I'll go PDF and then hit Save. And I think it will actually launch it in Acrobat Reader. Yeah, look, whoa, so quick I didn't even notice it. But this is now Acrobat Reader. See, it opened the reader. This is it. It's definitely a PDF. But more than that, let me go to my desktop. You'll see it on my desktop. Let me miniaturize this. There it is right there. And so lab number 4, it's got the Acrobat PDF icon, you know, and so there it is. So now all I have to do is either email it to myself, or maybe better still, just start my browser. I got Chrome right here. I could start Chrome. I could go to Canvas, and then I can send it on up. So that's the idea that I wanted you to see. Now, for those of you who's using Google Docs, if I remember right, I don't use Google Docs much, but I think to get the PDF, it's a little different. You don't go to the Save As. You actually go to Print. And then on the side you say Print As, and it says Print as PDF. So it's really doing a print to file PDF technique. So your choice in there. All right, but let's get back to the lab. So back to the lab, you'll see that I have the second one. Let me just show you the third one, but I'm not going to bother to print it up. Let's see or add it to mine. The next one says 90 degrees. Okay, so that'd be pi over 2. So really the only thing I need to do is to come over here and delete off the 3 and put a 2, click on done, and you'll see they're 90 degrees separate. That is, the blue one comes down and hits 0 like a sine wave, but the green one has been shifted over, so the green one looks like a negative cosine wave at this point. Okay? And then I would copy that and add it to my Word document here, and that'd be my third one. Here is the next one, and I said I wasn't going to do this, but it's kind of nice to see the last one, so I'll skip over the 120 degrees, excuse me, but I'm going to go to the 80 degrees, which is just pi. 180 degrees, which is just pi. Get a little hoarse for some reason. Okay, so then this is kind of nice to see, because one of the ones we wanted to emphasize is when they were perfectly out of phase, what we called perfect destructive interference. And so the first one, the blue one, goes up and the green one goes down. They exactly match each other, and the result is a 0. And so that is our destructive interference. As a side note, I just recently got a pair of noise canceling headphones. I've wanted them for years and years and years. I think in the video lecture I even talk about them. They're so amazing. In fact, I find myself just constantly, when I put them on to like read, I'll just put them on with no music. So I'll, won't even connect to my phone to play the music, and I just, it muffles out most of the sounds, and then you turn them on and it just goes dead silent. And I was like, wow. Anyways, really cool. And then, I can't hear anything reading, but it's just dead quiet. In fact, if I don't do anything, then it's kind of eerie. It's just, it really is eerie. If you're not reading or you're not listening to music, and it's just such a dead silence. You're like, oh, it's just weird. All right, anyways, I thought I would see that one. All right, so you make sure you do all 5 of them. Make sure you make a graph of all 5 of them. Make sure you copy all 5 of them onto your Microsoft Word or your Google Doc. And so at this point, you should have 5 graphs and hopefully a visual picture in your mind. And really what I hope is an understanding of what we mean by complex waves. And in this case, our complex waves are not that complex. Our complex waves are just made out of 2 simple waves. And these 2 simple waves are almost identical. They have the same wavelength. They have the same frequency. They travel at the same speed. They travel in the same direction. They have the same amplitude. The only thing different is they have a different phase. So this is a good start, but let's do something more interesting. And this is what part 2 of the lab is. Okay? And so let me go ahead and maybe turn off my graphical analysis, only to restart it with a blank new one. Okay? And we are going to make then this. Maybe it's best to show you on the board first. Let me find my marker and my eraser. And to help you understand a little bit more about superpositioning and complex waves, let's get into a real complex one. Let's do this. Let's actually produce a wave that looks like this. It is not sinusoidal at all. It goes up to its maximum amplitude and stays there. It drops down to its minimum or amplitude the other direction, that's negative, and then it just keeps doing that. That's called a square wave. And we can produce that with this fancy box we learned last week when we were doing our sound waves. Now, of course, when we did our sound waves, we just used the box to make a simple wave. Now, before we started the lab, I actually turned it on. I set the frequency to near 100. Looks like it's kind of toggling back between 100 and 99, so I'm probably like at 99.5. It's real sensitive, so I don't want to kind of touch it. Might be hard to get back there. And this electronic box then is sending a signal out here. Again, if you can remember from our sound ones, we ran these to a speaker. And we just sent a sine wave to it. But there is another set of buttons over here. And this button right here makes the sine wave. This one makes the square wave. In fact, I'll show you by putting it first on the sine wave. And the electronic wave goes here. And instead of actually feeding it to a speaker, I'm just going to feed it to the computer. And that's what this other electronics is. And so I've got the USB connected here. And the computer then will display it right on my graphical analysis. Now, to do that, I have to call up a certain program. And this is what you can't do on your at home because you don't have this equipment. And so let me collect the data for you and with you, right? I'm your lab partner here. All right, so as your lab partner, let me collect this data. So we've got this fancy box here, which is making the wave, and it gets sent into the computer with this fancy box. Now, you do have a computer, and you do have graphical analysis, but it won't do you any good without the hardware that connects the real world to the electronic world, the virtual world. But I have a nice little program that if I go File and Open, okay. Where did it go? Oh, my bad. Thank you, Ron. Ron's just pointing out that it's not, I've got the wrong program. I set this up in Logger Pro. All right, so another program, Logger Pro, is the one, it's just like graphical analysis, so you can see my confusion here. It's just like graphical analysis, except it's designed for a hardware interface to the real world here. All right, so let me try that again. Let me go to File, and let me go to Open, and the one I'm searching for is right here. It's called FFT, which, by the way, stands for Fast Fourier Transform. Remember at the beginning of this, I said this semester in Math 220, you will learn a mathematical technique. It's called a Fourier transform that gives you the mathematical skills to figure out what a complex wave is made out of. Watch, let's come back to the board here. My marker. Here's what I'm trying to say. That this complex wave right here is actually made up of a wave that looks like this, plus a wave that looks like this, simple wave, plus a wave that looks like this, plus, and so what I'm trying to say is, and trying to convince you, and this is the point of the lab, is that what looks complex, and it is actually made up of the sum of a bunch of simple waves. And to figure out what the amplitude and the frequency is of these, we have a mathematical technique called a Fourier transform. So let me encourage you, when you study that in your math class, to pay close attention. In fact, I guess you should always pay close attention to what you're learning in your math class. But this is a really powerful tool that you see constantly in the field of engineering and science. So this one, I'm not going to teach you the mathematical techniques. That's what Math 220 is for. But what I am going to do is just tell you that that algorithm is built into the computer program here. So we don't have to actually do the calculations to find the frequency and the amplitude that make this up, but the computer will do it for us. And as you'll see, when the computer does it for us, the computer will say, wait a minute, it's made out of an infinite number of them. How many do you want me to do? Because I can't do all infinite of them. And that's true. So I'm going to set the computer up here to do just the first 10. And you'll see that the amplitude goes down. And I kind of represented that in my drawing, maybe not very well. But I tried to draw the first one with the most amplitude and a little bit lower and a little bit lower. And that one didn't quite look lower. But you'll see that we'll just do the first 10. And the amplitude gets smaller and smaller. And so by the time we do 10 of them, the ones beyond that, even though there's an infinite of them, don't contribute that much. Because here's what I think is really cool about this lab, is we're going to do this. We're going to actually make this wave right here. We're going to send it into the computer. The computer is going to do the Fourier transform for us. So we won't have to worry about the mathematics part. But then the computer will tell us what is the frequency and the amplitude of the first 10. Because then what I want you to do, and I guess we'll do this together, is to then go to graphical analysis and put all 10 of them together, like we just did in part 1, where we put only 2 of them together. I'm going to ask you to put all 10 of them together. And then plot the result of those 10. And hopefully you will be pleasantly surprised that when you put all 10 of them together, you will get something that looks a little bit like this. And so will it be a perfect square wave? No, it won't be perfect. Because remember, we're only doing the first 10. But that's quite a few. So I think by the time you put 10 of them together and see this, you'll be quite impressed. You'll be impressed that literally this square wave is really made out of a sum of a bunch of simple waves. And even though we've only done the first 10, that's why when we do the first 10, it will only look kind of squiggly. It'll look very, very close. And you can kind of get the feel at that point that if you went on and instead of doing the first 10, you did the first 100, the more you did, the more it would look like that square wave. And that is the lesson of chapter 18, and the lesson of this lab is, what is a complex wave? A complex wave is really nothing more than the sum of a bunch of simple waves. It's why you'll see when we study waves, we always study sine waves. Why? Do we always have sine waves? It's a loaded question. Because you might say, no, we might have something that looks like that square. But I would say that square is made of a bunch of sine waves. And there's not a single pattern you can't give me that I can't tell you it's not made up of a bunch of sine waves. And so that's why you'll see in these 4 chapters, and when you go on to study, say, electronics or optics or acoustics, anything involving waves, you will always study the sine waves. Because what we know is we can always start with something that's real complex. Oh, like if you look out on the ocean here, it's a really complex looking pattern. But here's what I know. I can take that complex pattern and it is a summation of a bunch of sine waves. And so the only thing I need to study to understand my oceanography is sine waves. Even though they don't look like sine waves, that's because they are a summation of a bunch of sine waves. That's the result. Okay, so let's actually go back to the experiment here. All right, so back to the experiment here. So that's why I'm selecting this fast Fourier transform. All right, so I'm going to hit open, and you'll see what I get here. And when I open this, I've got 2 graphs. The first graph is actually the wave we are measuring. And the second graph is what we call the Fourier transform of it. It's actually the fast Fourier transform. In case you're wondering, really quite a brilliant design by some computer science people. Took the mathematics that you're going to learn in your 220 for Fourier transforms and figured out that if you had data points that were in powers of 2, so binary, they could actually make a really fast algorithm. And it's much faster than a regular Fourier transform. So we have Fourier transforms, but then we have fast Fourier transforms. The disadvantage is it only uses the data that is in powers of 2. So let's say you have a data set with 100 pieces. Well, 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64, times 2 is 128. Oh, too big. So it will only take 64 of those 100 data bits and do a fast Fourier transform on it. So you lose some of your data, which loses in quality, but it does it real fast. So in that case, you'd be better off to make 128 measurements and actually get some decent and fast results. Anyways, but that's a side note. And so I thought I'd throw that in there because you guys in computer science, you would love the algorithm. It's brilliant. Anyways, that aside, this bottom one then is the amplitude and the frequency. Okay? And I have it set here to show me the first 10. And it's going to show me the amplitude on this and the frequency here once it measures it. Okay? And so that's the whole idea here. Now, let me do this for a moment. Let me change my graph so that you can see it, I think, a little better to only 100 milliseconds. But let me also collect data for longer than that. The default is 700 milliseconds, but I'm going to go to 1200 milliseconds. Okay, so I'm going to collect as much data as this little box can hold. And I know from experience that this little box can only hold enough data to 1200 milliseconds, taking 10 samples every millisecond. Then we run out of storage for it. That's as fast as it can operate. But so you can see it better, I want to show you. Now remember earlier, before I got in this long discussion about what a complex wave is, I set this machine for a simple sine wave. So watch this. If I click collect, it'll take a while. But what I hope you see is a nice sine wave across the top for 100 milliseconds. It actually measured for 1200 milliseconds. Okay? But then down below, it made a plot of the different frequencies that are here. Well, I'm trying to convince you there's only one frequency here. This is a sine wave. This is a sine wave of 100. See, there it is, right there. It's saying this is its amplitude, this is its frequency. There's nothing else on here. And that makes sense because I fed in just a single sine wave. Okay, so now part 2 really begins here. Let me change the setting to a square wave. Okay, so I have square wave. Let me just check something before I collect data again. Let me make a graph that is 1200 and make sure it collected it all. Good, it did. In fact, I'm going to do one more. How about 1300? Okay, good. So it did collect it for the 1200, even though I only displayed it for 100. And that's what I'm going to do again. Let me collect a square wave now. And on the top, I'll display just the first 100 milliseconds. And I'm going to hit collect. All right, so here we go. Here's part 2 of the experiment. And so watch what it measured. Ah, there it is. Doesn't that look like a square wave? So this little box is putting out a square wave. And so here is the lesson of the lab. The lesson of the lab is, notice then that the computer, after doing a Fourier transform on this, is trying to say this. That right here, and there's a little tick mark here, 100 hertz has this amplitude. It looks like there's another wave that makes this up at 300 hertz. 500, 700, 900-ish, looks like it's a little shy of it, 900, 11, 1300, 1500, 1700, and there's the 10th wave at 1900. And so those are our 10 waves, okay? And so what your job is going to be after I help you, see, I'm gonna write down and help you collect what is the amplitude and what is the frequency of these 10. And then your job is going to be back to a graphical analysis and make 10 columns of these waves. And then make an 11th column, which is to add them all together. And hopefully you'll get that little green pattern that's very close to a square wave when you're all done. That's the idea here. All right, so let me grab my pen here, because I'm going to write these down. And this is where you would be writing them in a face-to-face setting, where it says write down the frequency and write down the amplitude. Let me just write them down, and then I'll put this in front of the camera so you can pause the video and see them. You might even be able to see them while I'm writing them, but won't worry about that. Probably best if you actually, Ron, put the camera on the screen here so they can see what I'm going to do here than my paper. So what I'm going to do here is come over here and say analyze my data, and I'm going to put this little box here that says examine, because if I move my cursor and I look right here where it says, okay, what is the amplitude? And it measures it in a voltage. But I'm going to look for the biggest one, because they're kind of close together. It looks like this one right here is the biggest one, 2.91. And I'll take that frequency. So that frequency is, and I'm surprised it's 101. But nonetheless, that's what I'm going to write down. So I'm going to write down frequency is 101, and the amplitude is 2.91. Okay, let me move my cursor over, and let's find the next big one. Looks like that, 70, 72, looks like right there. All right, so an amplitude of 72.6 and a frequency of 298. Okay. Let me do another one here for the biggest one. 38, 45. Okay, that looks like the biggest one right there. Okay, so it's got an amplitude of 45.7 and a frequency of 498. And so again, let me just take this as a moment to point out then that what I'm getting here is this is the computer telling me, after doing this fancy math, this Fourier transform, it's telling me that that square wave is really made out of this. And so the idea is you're going to try to convince yourself that it is, because you're going to take these 10 waves and type in 10 columns, make these 10 waves, and then plot them. And that's the part I'm going to leave to you. All right, but let me keep getting the data. In fact, I'm going to do something. You can see that these are getting kind of small, so I can see them a little better. I'm just going to change the size of my scale. So maybe I will put the top part here at 50, and then I can see these a little better. All right, so I just did the 500. Let me move over then to the 700 one right about here somewhere. Let me just kind of scroll over and scan my data. And it looks like 22, 33, looks like 33 was the highest one. Okay, so with an amplitude of 33.3 and a frequency of 697. Okay, good. Let's go over and get the fifth one here. And let's just look at the amplitude, 13, 24, looks like 24 was the highest one. So an amplitude of 24.8 and a frequency of 896. Okay, Whoops, my cursor moved on me. Let's do that. Okay. And I'll come over here. Okay, let's see. 1, 10, 20, 18. Okay, looks like 20 is the biggest one. All right. So this would be an amplitude of 20.4 and a frequency of 1096. Looks like it rounds up. Let's go to another one here. And let's look at the amplitude. There's a 3, a 12, a 17. Looks like 17.9 is the biggest. Okay, so 17.9 and a frequency of 1295. All right, let's do another one here. 15 look like the biggest. All right, so amplitude of 15.2, frequency of 1494. And 2 more. And that'll be our first 10. And that's what we'll work with. All right, looks like 12.8 is the biggest amplitude, so 12.8. And a frequency of 1693. And by the way, I hope you're seeing that the amplitude is getting smaller and smaller. That's what I was saying, that each one is less significant. Although the 11th one is, still fairly significant. That's why, we won't see a perfect square wave when we add these all back together. I mean, we'd have to do an infinite number of waves. But I think with just 10 is enough work and enough to see that the pattern is there, and you begin to learn about complex waves, that you're convinced that they really are made, that this complex waves are really made of a summation of a bunch of simple waves. It gives me a chance to kind of introduce you then to words like a Fourier transform, complex wave, superpositioning. All right, and then this last one looks like it has an amplitude of 12.2 and a frequency of 1892. All right, Ron, why don't you zoom in here on this, and I'll just hold it here, and what you guys need to do is probably hit pause and just say, all right, write this down, or copy it into Graphical Analysis, because you're gonna need all of these. And in fact, let me show you what you're going to need here. Let me kind of help set you up. I won't take the time, because it will take a little while to set all this up, but this would be good for you guys to kind of do on your own, is let's talk about just one wave. Now remember, you have to do all 10 and then add those together. So you've got a lot of columns to make. But I'll come over here and start the mathematics. And so remember, the equation for the wave is some amplitude times sine kx minus omega t plus a phase. So as you build these waves, let's do this. Let's plot them as we have recorded them. And here's what I mean by that. Let's come back to the equipment. The waves are actually traveling down this red wire. And as they travel down this red wire, my probe then measures the wave right there. And it measures it over a period of time, not position. See what I'm saying? So let's do this. To reconstruct this, let's call this connection right here x equals 0. And so we're going to plot the wave as a function of time. So what I have then is I'm going to say, let's call my measurement spot 0. So that one is out of the picture. Let's also say that the phase, since we can pick it anything we want, let's say we're going to measure it at 0 phase. I suppose maybe even to make it easy on ourselves, we could say our wires are the negative x-axis And so they would be traveling to the negative x-axis. So we would have a plus sign there. And so what I'm trying to say here is the equation that I'm going to put in is this, where omega is 2 pi times the frequency. And so what we need to do is make a column of time so we can plot it, and then put in the frequency and wavelength of each of these 10 waves that we just measured. Oh, watch. Let me get you started here. So this first column is going to become time. And as I look in the instructions, it actually says make that first column into time. All right, so let me do that. Let me come over here to the X and double click on it. Let me change it to time for the name. A long name I'll just spell out. Short one I'll put a T. Let's measure this in units of seconds. And like we did in part 1, let's have the computer generate the data. Let's start at 0, and let's see what the author says here. He goes to 20 milliseconds, 0.02 seconds. Okay, so we will go from 0 to 0.02. Okay. And our spacing, and so he gets a lot here. He says make the space size point, and he's got 4 zeros and a 2. So point, 1, 2, 3, 4 zeros and a 2. So this will make 1,000 places on the x-axis. Okay, so these are going to be closely calculated together. And we probably don't want to, but I will nonetheless. Scroll down to 1,000. Yeah, there it is. All right, but let me come back to the top. Because here, like we did in part 1, it's time to make a calculated column. And let me just kind of help you get started by saying, why don't you just call the first one wave number 1, and you can call it W1. The units, well, they're not really volts, and they're not really nanometers, but I'm just going to call it nanometers, like it was we were feeding this into making a sound wave like we did last week. So it's really electronic waves here. All right, but I'll just call it nanometers. But here's the big thing. This is the big thing to show you. What is the equation? And as I was trying to show you then on the board, it would be the amplitude multiplied by sine omega t. So I'm going to come back to my data. My first wave says the amplitude of the first one is oh, I totally wrote this down wrong. I apologize. You guys probably noticed it. I only wrote it as 2.9. I bet that was 200. Let's go back. My apologies. I totally wrote that one down wrong. That was way up in the 200s somewhere. Yeah. Let me try this again. What did I do wrong? Oh, I see what I did wrong. I stopped on the wrong one. Okay, good. I hope I didn't make another mistake here. Maybe I should scan my data. But this first one is definitely wrong. So, first one has an amplitude of 232. And oh, I see what I probably did wrong. I didn't see the decimal place, I bet, and I read it in my mind as 291, thinking that was the biggest. And so, my apologies. So it's 232 is that first one. So scratch out that 2.91 that I must have thought in my head was 291 was the biggest one. Looks like the biggest is 232. Okay, so with that in mind, let's come back to the graphical analysis here. And so I can put in the amplitude of 232. I can then multiply that by, so here's going to be that first wave. Let me go to my trig functions, sine. So here's sine. And then as we just put on the board, it would be 2 times pi, 3.1415, times the frequency that I recorded. Okay, so the frequency is 101. Oh. And I said that 101 was bothering me because it just seemed like it should be at 100 or a little below 100, not at 101. I was on the wrong one. So the frequency's off too. All right, my apologies again. Let me come back here. Back to Logger Pro. Yeah, not only is it the amplitude, but it's going to be a slightly lower frequency. Much better. I feel much better now. I should have recognized it. Okay, there we go. 232 at 99, and looks like it rounds down to 90. I'll 99.5. Why not? And so, again, let me say it. My first one, when I held this up before, I showed you wrong. It should be a frequency of 99.5 and should be an amplitude of 232. Okay. And now as I scan my frequencies, I like those a lot better, and as I scan my amplitude, so everything looks good, and we'll find out. In fact, I'll even make these graphs before I send this out, so I don't want to take the time during the video here, but in case there's something wrong, I can explain that. Okay, so let's come back to the graphical analysis. And so the frequency is 99.5. And if I hit done, sorry, didn't finish my equation. I'm having a little hard time here. All right. So multiplied by time. All right. So variable time. Done. All right. So I should have this long column. And if I went to plot it, and so here's wave 1. I would have, and now here is the point protectors as we saw. Let me turn off the point protectors and connect the lines like we saw in part 1. There it is. Okay, so there is 2 cycles. Okay, and so we're plotting the wave as it would come by with 2 cycles. And so there's wave number 1. Now again, let me not do all 10 of them. This is something I think that you should do, and you probably don't want to watch me do 10 of them. But let me get you started. Let me at least do the second one, and then we'll move on in the lab here. But watch this. If I do the same thing, if I go data, new calculated column, and then just type in wave 2, and W2 for short, units of nanometers. Let's come here. This is where I'm going to go to wave number 2. And so my second wave will have an amplitude of, and it'll be 72.6 multiplied by sine 2 times pi times the frequency. So the frequency of this wave is 298, and then times the variable time, and click done. And so you can see that the computer made wave number 2. If I go to more and plot both of them, you will see this one has about 3 times the frequency. In fact, if you take a moment and think about this, you'll kind of see why this is going to end up coming out as a square wave. Look at this green one. The green one and the blue one are saying up, but when the blue one gets really tall, the green one say, no, come down. And then it gets tall again. So these two together are saying lift this edge up and bring that top down. And so we're starting to form a square wave. And that's the beauty, I think, of this lab, is you begin to see that, hey, this square wave really is a composite of a bunch of sine waves. Now, I said I wouldn't do more, and I'm not going to do the third one. I promise It's tempting as I am. But let's at least do column 11. Okay, so your job is to put in all 10 of these, and column 11 is to add them together and see what you get. See what the composite is of all 10 of these. Let me at least make the composite of these two. So let me make column number 11 for you. And so I'll go new calculated column, and maybe I'll just call this total wave, like I did before. And call it short name TW and units of NM. But it's really easy to do the mathematics of the superpositioning. All you do is you add them together. Now I'll say when you add them together, you're going to have 10 waves. So you got to add all 10. But I only have 2 right now. So I'm going to go variable, and I'm just going to go, okay, wave number 1, and then hit plus. Wave number 2. And then, of course, you would go plus wave number 3, plus wave number 4, plus wave number 5. But let's take a look at the composite of these two. And I'll hit enter, and so you'll see kind of the burnt orange one right here. Okay, so this is what it looks like. And to put it on the graph, I've got to click on the vertical column and select more, and then do total wave and see what I get. And so you can begin to see that this burnt orange one is still a long way from looking like a square wave. Right? You have to do an infinite number to get a square wave, and even when you do 10 of them, it'll look very close to a square wave, but still won't be that great. I've only done 2, but I can begin to see how the orange one goes up, kind of leveling across, come down, kind of leveling at the bottom, and I'm beginning to see the shape. And so if you put in the 3rd one and look at it, the 4th one and look at it, the 5th one and look at it, I think you'll be pretty impressed. You'll be going, wow, this is getting more and more like a square wave. Your job is to ultimately get all 10 of them in there and then copy and paste that result onto your Word document and make it a PDF and turn that in. So way back at part 1, we did 5 graphs, so you should have 5 graphs, and so this is your 6th graph. Okay, so right now you have 6 graphs on your PDF, and you got 1 more to do here. So let's do this same thing 1 more time. Okay, and here's what we're going to do. Maybe I'll draw a picture over here, but to get the idea, we are going to do the same thing here in part 2, but for a different shape. And the shape that is easy to make for our equipment is what we call a triangular wave. So we are going to make a wave that goes up and then down and then up and then down and then up and then down and then up and then down. So you can see why we like to call it a triangular wave. But let me just say, in case you missed it after the many times I have said it, let me say it again. What's the point here? The point here is to show you that if we actually make this wave and then we measure it with the computer and we let the computer figure out what the amplitude and the frequency is of the first 10 of them, and then if we plot those 10 together, we will hopefully see this result. And that is hopefully my way of making you go through a procedure here that will convince you that any shape, give me any shape you want, I can write it as a sum of simple waves. So a sum of simple waves make a complex wave. And when you go from a complex wave to its components, that mathematics is called a Fourier transform. Now, we haven't learned that yet, so we're not going to do about the math. That's why we're using the computer to do the math for us. But what I want you to do is the other way. Once we have actually then made the wave and then let the computer tell us what the amplitude and the frequency is, then we're going to go the other direction and we're going to plot those 10 and see if we get something close like this. But I will say, you're going to see the same thing here where there's actually a triangular wave made out of an infinite number of waves. And I've asked the computer to only do the first 10. And we're going to write down the first 10 so that you can do the same thing with the triangular wave. And you're going to see something that looks like this. When you put all 10 of them together, you're going to see something that's pretty straight and kind of round. A little bit round, a little bit. And so one lesson you might get out of this is it's these higher frequencies that do the sharp edges. We saw the same thing for the square wave, where the square wave, you know, we kind of saw some wiggles up at top. We didn't see nice flat and a square. And same thing, we won't see pointy edges. They'll be rounded off a little bit. Okay, but let's give it a try. All right, so I'm going to come back over to my equipment. Let's come over here to Logger Pro. Now, as you can see, I have my data before. Let me switch my equipment. And so I'm going to push in the other button that says triangular wave. There we go. And so I'm essentially going to have the same time, the same measurements, and it will display the wave up on the top graph, and this bottom one is what we'll collect our data with. Okay, so here I go. Let me hit collect, and it will take a little bit. It's got to record it and then analyze it. All right, so again, this is our last graph. I know I've been talking for a while, so good news here. This is our 7th and last graph that you're gonna turn in here. But there it is. There's what the computer recorded. Okay, so the computer recorded a triangular wave, and it actually went not just 100 milliseconds, but went, as I said, to 1200 milliseconds. So you can see it a little better. I want to display it here as 100, and then it's got the first 10 out here. Sadly, at this resolution, you may not be able to tell. There's one wave, there's two, there's three. There's 4, 5, 6, 7, 8, 9, and 10. But they're really small, so I'm going to have to change the resolution, and I will do that after I make my first measurement here. Okay, so I'll start writing these down, and when I write all 10 of them, then you can copy them down, because your job will be to take these 10 waves, put them into graphical analysis, add them all together, and see what you get. Okay, so I shall begin here. All right, so let me move my cursor. Oh, I guess I got to put examine on first. All right, so let me turn on the examine marker. Let me put this here. Let me scroll over. And let me find the biggest one and hopefully not mess up. 141, 135. So it looks like the 141 is the big one. So I'm going to go amplitude 141, and frequency is 99.5. Not a surprise, same frequency. That's what I haven't changed anything there. Okay, so now I'll move on to the next one, but like I said, it's a little hard to see because it looks like it only comes up to about a 10. Maybe a little higher than that. So let me put the top of the scale at 15 so I can see it better. And so right here I'm going to put 15. Oh, and that was a little too low. Let's do 20. Okay, now I can see the top of it a little better. All right, so there's the second one here. And let's look for its biggest amplitude. 5, 14, 16. Looks like 16.2 was the biggest. All right, so an amplitude of 16.2. And catch this, because you would have no way to know this from anything I've said or even what the computer has shown. This is a negative amplitude. This is a negative 16.2. And so when I show this results to you, I'm going to show you that you need to type in a negative amplitude. Okay? Now, sadly, our simple program doesn't show it. I have to know it because I know Math 220. I know how the algorithm works. This plot is actually plotting only the absolute value. And it said 16. Doesn't that look a little... No, that looks like 16. Okay. But it plots only the absolute value. And I didn't say anything about it when we did the square wave, because the square waves, they always come out positive. But for the triangular wave, they alternate, plus, minus, plus, minus, plus, minus. And so I need to tell you that and write that down. Otherwise, when you add these 10 together, you won't get a triangular wave. You'll get something that kind of looks very close to a sine wave. In fact, that's kind of my wave when I walk around the classroom and students are working on them, and I kind of see that They go, oh, mine doesn't really look like a triangle. It looks kind of like a sine wave. I go, yeah, I know what you did. You didn't alternate the signs of your amplitude. Because it's easy to miss that. Because there's nothing that I have said up to this point, and there's nothing in here that says it. And unless you've gone through Math 220, you won't know that it's supposed to be negative. So I'm telling you, it has to be negative. You'll learn the math soon. All right, so I'm going to write down negative 16.2. And the frequency is 298. 298. Which was the same we got for the square wave. Doesn't surprise me. In fact, I would be surprised if any of these frequencies are different than what we got for the square wave, since I didn't change any frequency. All I did was change its shape. All right, so I need to find the biggest one. Let's see, that was almost a 6. And it looks like that's the biggest one, almost 6. Okay, so this is an amplitude of 5, and it'll be a positive 5.94. And its frequency is 496. Well, that's off by 2 from the square wave, but off by 2. I won't think of that as a problem. Okay, we go to the next one. 3. Looks like the 3 is the biggest one. So 3.08, but it's minus 3.08. So that's a negative amplitude. And it is at a frequency of 695. All right, let's go to the next one. In fact, just so I can see it a little better, I'll make even this bigger. Okay. So let's go to this one here, get some data for you. This has an amplitude, looks like 1.86 might be the biggest one. And this was a positive. 1.86 is the amplitude, and the frequency is 893. Okay. Let's go to the next one here. Scan across. That might be the biggest one, 1.24. Okay. And that would be a negative. So an amplitude of negative 1.24 and a frequency of 1091. Good. Okay, might even make this even bigger still so I can see it a little better. Okay, so that was at about 11. So we should be this one, just shy of about 1,300. Okay, so let's look for the biggest amplitude around 1,300. Looks like the 0.8 is it. Let's go back and forth. Yeah. All right, so there's the biggest one. 0.873 is the amplitude. It's a positive one. And a frequency of 1,290. The next one, which is going to have a negative amplitude. Looks like the biggest is 0.6, huh? Okay. So negative 0.633 is the amplitude. And the frequency is 1,488. Hang with me, 2 more measurements. And so here we have 4748. So that one might be the biggest one right there. And so this would be a plus amplitude. And so it would be a plus 0.482 for the amplitude. And as a frequency of 1,687. And last one has an amplitude of, looks like that's it, 398 is the biggest one. It'd be a negative. So negative 0.398 for that amplitude. And a 1,885. Good. And I'll hold this up so that if you didn't catch all that when I was saying, and Ron, if you want to kind of zoom in and get it to focus, and then you don't have to stay long because they can hit pause. So students, you guys can hit pause. Did it focus? Okay. And then you guys have to fill that in. Now, I will tell you at this point, this last graph should be pretty easy for you, because here's what you're going to do. If you just go back to your graphical analysis, your data table should be already, and remember, I didn't do all 10 waves, but at this point, you should have all 10 waves, and your 11th column should be this total wave. And of course, you should have something that looks like something like a square wave. So all you need to do is to go back and edit wave 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And you don't have to change much. All you have to do is change the amplitude and the frequency. And of course, remember to put in a negative amplitude where it's appropriate. So 5 of them should have a negative amplitude, and the other 5 should have a positive amplitude. But then once you put in all 10 of those, plot it, and I hope you will see what I was saying earlier, that you'll see what looks very close. It's got rounded points to it, but very close to a triangular wave. And so I know this part 2 is kind of long, but I hope by doing the square wave and the triangular wave in part 2, by actually creating the waves here, and then letting the computer tell us what the amplitude and the frequency is, and here's the best part, you then taking that amplitude and that frequency, and you putting that in and adding 10 of them together. And I know it's kind of busy work to add all 10 of them together, but I hope you will walk away saying, I'm getting the idea of these complex waves. I'm getting the mathematics of a Fourier transform. I know what we mean by superpositioning. Superposition is just simply saying that any complex shape, any complex pattern is really a summation of a bunch of simple waves. Which is why, as you go through your science and engineering education, we will constantly study our electronics. Those of you who did 122, you'll remember that when we did our AC electronics, we only did sine waves. And you could have asked, well, what about the digital world? Don't we send square waves? We turn up pulses, on, off, on, off. How come we don't study that? Why do we just study sine waves? And my answer is, we did study pulses. Because if we know how to do sine waves, a pulse is nothing more than a summation of a bunch of sine waves. And that's hopefully what you're getting out of this physics lesson of complex waves in chapter 18, and also what you're getting out of your math in Math 220. All right, well, we're done with the lab. Remember, those are the 7 graphs. Put them all into one Word document and save it as a PDF and upload it into Canvas before Sunday night. All right, take care.